There is another factor called first flush effect. First flush effect means what it means that when there is a rainfall, you might expect that pollutant concentration is very high at the very beginning. Another way to think of in your rooftop water. If you collect a bucket of, if you put a bucket below your rooftop where the water is dropping, you see that a lot of this debris that is initially there is being flown into the system or in your collection. So that first flush is essentially that. In the very beginning, all the water and the initial rainfall water is going to flush out any pollutant at the very beginning. So that means the concentration of pollutant is expected to be very high in the beginning. But how long after the rainfall? It varies based on pollutant types as well as the land, the catchment scale. So here is examples. As you can see that this is the concentration of different pollutants. As you see that here, now COD concentrations, DOC concentrations, oil and grease, change over time. This is very basically the peak flow appears at a certain time of rainfall. Whereas if you think of the COD and DOC, the concentration peak much earlier. And so this is this is the flow. This is the oil and grease, and this is basically peak flow over here. So that means peak flow appear here. The peak of pollutant is much before that. So this is what we call first flush, means it comes out much faster. And again, the reason is because accumulated pollutant are washed up initially and leaving behind less pollutant later to be washed up. So that means that because of dilutions, you'll have low concentration later. Why is important? Because if you know what time you are getting a lot of pollutants, you can treat that water. If you remove the first flush water reaching from the surface water, you will be able to remove 90% of pollutants in many cases. So green infrastructure design is based on the first flush phenomenon. That's why now if you and there are times when you may not observe first flush. For instance, smaller catchment area less likely to mix during discharge. So that means you are going to observe first flush. If once it makes quickly, then for a long time, then you will not be able to see a distinct peak. So this is the picture you can see in the very early TSS concentration was very high, and then as years go, it's become lower. And this volume is also first flush volume. And you can see that for some pollutants will have a distinct first flush effect. Some pollutants may not. For instance, first flush of particulate matter is common because higher flow rate and generally found earlier in the events. Because all the erosion happens, seed flow and everything will remove a lot of particulate matter. So that means you most likely you're going to see that in the beginning. And also higher flow means higher energy that is going to disperse much more pollutants. More soluble pollutant exhibit first flow effect more so than the suspended matter. Again, soluble pollutants because initially water flow rate is low. As you can see over here, water flow rate is very low, but it's enough to dissolve a lot of pollutants. So the concentration is mass of pollutants per volume of pollutants. And so again, that means if your volume is low, your for instance, your concentration is basically mass of pollutants by volume of water. Initially, volume is low at initially volume is low. That means, and also there are a lot more source of pollutants. So the MP is much higher. So if MP is much higher, volume is low initially, the C is much, much higher. So dissolved pollutant concentration could be much higher because of that reason initially. So how do you calculate, identify first flush effect? Is basically you are comparing how much pollutants is discharged at different fraction of the water compared to the total amount of pollutant discharge. So you are basically comparing mass of mass ratio. So this is the M ratio is mass of pollutant discharge at certain time of the rainfall divided by total mass of the pollutant discharge in the entire events. You add them together. And relative discharge is the same thing, basically volume of water discharge in that time divided by volume at different entire volume that discharge in the entire events. So if you compare those mass ratio to the volume ratio, discharge ratio, or relative mass of pollutant discharge to relative water discharge, they are proportionally with each other with a factor b. And so if you do the logarithm scale, you'll get that b value over here. And if you plot the log value and all that, you can get a number. So for instance, here, if you see this value, v value is less than 1. So this looks like a curvature. That means there are more pollutant discharge initially per volume of water. So if this is phos plus, and if it's a straight, ideally it's a straight, it should be equally. Every time the water should be discharged similar amount of pollutant. It's not the case. In this case, the discharge is much higher. So all you have to look for is the b value is less than 1. This is going to be a phos plus. So how do you calculate it? This example questions, this basically it gives the concentration at different time and the volume, and you are going to calculate that. So these are the TS. This is the for volume. This is for TSS mass, and you are going to calculate whether there is a phos plus or not. Again, what you see over here is the time duration, so you can know the durations, and this is del Q times delta T, or the volume of discharge. And if you do the cumulative volume, you then add them together, then you get the different volume at different times. So this is the total volume, and that's basically the amount of volume discharge. So what that means is at different time, you know how much volume discharge, how much fraction of that total discharge is calculated. So here this one is basically VT by V. So if you do this by this, you get that numbers. So this is going to be, this is basically 5040 divided by 19800. So you get the number, and then if you take the log value, you get the answers. Same thing for mass. At different time, you know the concentrations, you multiply this value, and you get the total mass of pollutant discharge. And then if you do the total mass, this is become this much volume. If you divide that one, and you get the value MT by multiplying QC. So this number is given. So this is milligram. And this is cumulative, by the way. So if you do this one, MT is basically MT divided by M, which is this M. You get a fraction. So now you get a log. So that means what that means is only 2.6% of the total mass is discharged in the very first flow. Here, if you see 0.25, only 0.25% of water. So that's very close to 1. But here you can see that 0.63, that means 66.3% of the pollutant discharged in the second time you take water. And here 95.9.5%. So if you took the log and you did a transform, what you got is basically that slope is 1.09. If you take the slope, that's basically that is 0.19. And y-intercept. Cumulative might slightly. So because it's less than 1, so this basically slightly lag behind. Here the slope is different. So that means you can see that here, this is the slope is less. All right, so check the examples and then you'll be able to explain this much better. All right, let's take the quiz. The quiz is the peak flow of pollutant concentration come after the peak of discharge rate. The answer is true or false. Take a pause your video so that you can have some time to think. All right, so I hope you pause it. So the answer here is that peak of pollutant concentrations come before the peak of discharge rate, because usually a lot of times earlier you get the most polluted. So this answer is false. And we learned that here was the case because of the earlier the pollutant source is much higher, it's less diluted, so they get much more high concentrations.